couple minutes here, no, sorry, a couple seconds here before the sound kind of kicks in, because I've noticed on this app, the sound doesn't start right away. So just a couple of reminders. So here's Tuesday, 3:31 today. And remind you guys, if you have not, take care of this at Whiteboard Mr. P. Follow on Twitter. It's going to use it to kind of mirror things as we go through these weeks to post messages. So today, Tuesday, 3:31, again, I'm going to post this on the forum once I have the link, because I'm making the link right now on the YouTube link right now. You guys will need to, at the very least, state your name and period for check-in, ask any questions about the Lewis worksheet that you began your work on. I'll be available in the forum for immediate responses. And then you're going to view this video lecture and take notes on today, talking about formal charge calculations. So that's what we're doing right now. And then again, tomorrow, I need you to submit your Lewis worksheet in really any digital format. If you can scan it, great. Or if you can submit me a picture. Again, I just don't want 16 pictures. I want it to be condensed, easy for me to read and look at, you know, 1 or 2 pictures, that kind of thing. Do your best with that. But the bottom line is I need it by class period tomorrow on Wednesday. Should be able to get things kind of graded and turned around and talk to you about it. Then we'll kind of go over some things on that on Thursday when we check in, and we'll have our next link and next video lecture going on Thursday. And then again, the quiz is on Friday on Lewis structures. So, all right, so here we go. Today, again, formal charge calculations. So, what's formal charge? Basically, think of it as another way for us to be able to kind of predict the more likely Lewis structure when there are potential multiple possibilities. Because as you guys have been working on these and we've been introducing them to you with these Lewis structures, you've probably kind of noticed a little bit that sometimes you may come up with 1 or 2 or maybe 3 different ways that maybe seem to work and you're just not really sure. So formal charge calculation is a way for us to be able to ultimately predict which one's the better version, right? Or the more potential version when you're coming up with different ways to construct these Lewis structures. So think of formal charge as basically a designation of the distribution of the electrons that are either bonded or unbonded around the atoms that are involved in the bonds within the Lewis structure. Right? So again, we're looking at primarily, this is geared for covalently bonded molecules or covalently bonded structures. So we're talking dashes, right? So using dashes to show shared pairs of electrons. And then it says right here, right, the hope is to have the most zero formal charges for all or almost all of the atoms in the structure. And that's going to be pointing us to the most likely bond / structure of the options that we're creating or given. One thing I want to say is that formal charge calculation, we're going to get into how to calculate in just a second, is not, you're going to look at the formal charge calculations for individual atoms within the molecule that you propose, and it is not a total. What we're looking for is we're looking for the option that has the most or all of the atoms have a 0 value for the formal charge. And a 0 value designates that the electron distribution is correct according to the number of valence electrons that it has originally, as well as the number of electrons that it has the potential to want to share. Another way of me saying that is, how many bonds does it want to make? Okay. All right. So let's move on with kind of how to calculate these right now. So the formula for formal charge calculation. So CF stands for formal charge. Okay. There's this X, Y, and Z. Okay. Well, what's X? X is the number of valence electrons in a free atom, which is equal to the last digit of the group number in the periodic table. So again, this is kind of a long-winded way of me saying, like, so X, the X value is for carbon, right? Carbon is in group 14, okay? It has 4 valence electrons. It's got 4 valence electrons around it as a free atom, okay? So it's X, the X value for carbon would be 4, okay, as a free atom, not bonded to anything. The Y value is the number of unshared electrons owned exclusively by an atom in the Lewis structure. So this would be like, say, an example of like chlorine that forms, it's in group 17, it likes to form a single bond. So chlorine will form a single bond with some other element over here. I don't care what else it is. But chlorine has these total of 6 unpaired electrons or unshared electrons. So chlorine's bonded to something else over here, right, forming a single bond. The number of unshared electrons owned exclusively by the atom, in this case, chlorine owns 6 electrons exclusively. So in this little scenario here that I've drawn up, excuse me, the chlorine atom has a Y value of 6. And then the Z value, okay, this is the number of bonding electrons shared by an atom in a Lewis structure. Okay. The number of bonding electrons would be, in this case, for chlorine, if we're looking at calculating the formal charge for chlorine in this example, the number of bonding electrons is 2. It's connected by a dash to its neighbor, right? So it therefore has 2 2 bonding electrons that are being shared. So its Z value is 2. Okay. So let's maybe take a look at this like example right here real quick that I've just drawn up and kind of walked you through. So the X value for chlorine's in group 17. It has 7 valence electrons as a free atom. So if chlorine in this little scenario down here, right, has 7 valence electrons, X value is 7. The Y value, okay, the Y value, the number of unshared electrons owned exclusively by the atom in the Lewis structure, is 246, 6. Okay. And then the Z value, the number of bonding electrons shared by the atom in the Lewis structure. Chlorine here in this example, again, we're calculating formal charge for each individual atom in the Lewis structure, has a Z value of 2. So it'd be Z value of 2, and that's divided by 2. So we got inside the parentheses in our calculation here, 2 divided by 2 is 1. 6 plus 1 is 7. 7 minus 7 is 0. Okay, which is good because this is kind of goes with expectation. Like chlorine, we know that we kind of have an expectation that it wants to form 1 bond. So in this scenario, this is showing what is sort of expected. Now, in choosing the overall Lewis structure of whatever this whole thing is, we need all this other information, right? What's the rest of the molecule? Okay, so let's look at an example on page 188. So you guys want to flip to your books to page 188. Okay, and here it is. So here's 2 whatchamacallit, potential structures for this stuff called methyl alcohol, right? Methyl alcohol is CH4O. So here's option number 1 and option number 2. Okay, so option number 1 and option number 2 have been proposed. We've gone through, created our Lewis structures for these 2. And what we want to do is just decide which one's sort of the better of the 2. Okay. So as we're looking at this, we calculate the formal charge for the carbon in this example. Okay. So the formal charge for carbon in this example, the X value, the number of electrons in a free atom of carbon, is 4. The Y value, which is we'll flip back and forth, the Y value is the number of unshared electrons owned exclusively by the atom. Well, carbon doesn't own any unshared electrons, so it's 0. And then the Z value is the number of bonded electrons shared by the atom in the Lewis structure. So it's got a total of 2, 4, 6, 8. Okay, let's do this quick. So 2, 4, 6, 8. So X is 4, Y is 0, Z is 8. 8 divided by 2 is 4. 0 plus 4 is 4. 4 minus 4 is 0. Do the same thing for the oxygen here, right? Okay, the oxygen right here, oxygen as a free atom would have an X value of 6. It's got 6 valence electrons. The Y value is 4. It's got 4 electrons that it owns exclusively, 4 unshared electrons. And then it's got a total of 4 shared electrons among its 2 neighbors. So 6 is X, 4 is Y, Z is 4. 4 divided by 2 is 2. 4 plus 2 is 6. 6 minus 6 is 0. Okay. Now you'll notice, right, they didn't calculate the formal charge for hydrogen in either of these cases because it's 0 for both. Right? So hydrogen, if you any one of these hydrogen examples on either of the 2 structures, I know we're on structure number 1 right now only, but the hydrogen here, X value of 1, Y of 0, Z of 2. So Z 2 minus 2, 2 divided by 2 is 1, 0 plus 1 is plus 1, 1 minus 1 is 0. Okay. So all of the hydrogens within this are 0 as well too. So anyway, in structure number 1 over here, all of the formal charges for each one of these atoms in the proposed structure are all 0. Okay. So, we're going to kind of lean ourselves on this is probably the correct Lewis structure. But before we do that, we'll look at obviously structure number 2. So, I have this little note here, some common sense, right? Now we can kind of look at this, but I'm using this example, and the book uses this example to merely kind of prove a point. There is some common sense to apply here from what we've talked about. Like carbon has 4 valence electrons, so we know that carbon has a tendency to want to make 4 total bonds. Well, in this picture, it's only got 3 total bonds. That's a little weird. That should raise a red flag, right? We know that oxygen is in group 16. It's got 6 valence electrons. It's 2 short of an octet. So we know that oxygen has a tendency to want to make 2 bonds. But in this case, it's showing it with 3 bonds, right? So that should raise a red flag in your mind as well too. But if you laid out the Lewis structure for this, we still got the same number of it. When we talk about writing Lewis structures, it's all about total number of electrons. The number of electrons is identical. There's 2, 4, 6, 8, 10, 12, 14 electrons here. 2, 4, 6, 8, 10, 12, 14 electrons here. For all intents and purposes, we got this sort of works, right? Quote unquote works. But when we calculate the formal charge, let's go ahead and do that. Okay, so here's for carbon right now, the carbon in the middle here. The X value is 4. The number of valence electrons in a free atom is 4. The Y value, which is the number of, back again, number of electrons owned exclusively by the atom. Well, that's 2, okay, 2 electrons in this depiction. And then Z value is the number of bonded electrons, 2, 4, 6. There's 3 total bonds, 6 total electrons. So 6 divided by 2 is 3, 2 plus 3 is 5, 4 minus 5 is minus 1. Okay. Oxygen, same thing, right? So here's the oxygen now in this structure. 6 valence electrons is an unpaired atom. How many does it own exclusively by itself? 2. Z value of 6, 2, 4, 6 bonded electrons surrounding that atom. 6 divided by 2 is 3. 2 plus 3 is 5. 6 minus 5 is plus 1. Okay. So we have these 2 atoms both here having non-zero values for their formal charge. The carbon has a -1 charge. The oxygen has a plus 1 formal charge. -1 formal charge, +1 formal charge. All the hydrogens are zeros, right? They're good to go, okay? But again, there's some common sense here, right? And this is why we're seeing these numbers off. They're non-zero values because this proposal that was created, that we're using as this example, has situations where it's going against what carbon has this tendency to do. It's going against what oxygen has its tendency to do. Atoms have tendencies to want to get to octets. They have tendencies in terms of how many bonds they want to create. And in this case, we're kind of, I don't know, for lack of a better term, we're trying to put a square peg in a round hole. We're trying to mishmash this together and going against the rules of how carbon has a tendency to create 4 bonds. Oxygen only has a tendency to create 2 bonds, okay? So let's kind of read through some of these things that I've highlighted down here. So ordinarily, the more likely Lewis structure is the one in which the formal charges are as close to 0 as possible. So we're looking for the one that has the most zeros, okay, in comparison. So applying these rules, we can see that structure number 1 for methyl alcohol is preferred over structure number 2. Because structure number 1, all of the atoms listed are 0 values. Okay? Structure number 2, there are 2 atoms that have non-zero values. Okay? And remember, formal charge, what is it? It's a way for you to be able to make a designation about how are the electrons being distributed around the atom. A designation of a formal charge of 0 is an indication that the electrons are distributed correctly. It has the correct number of original valence electrons. It has the correct number of bonded electrons, and it's creating the correct number of bonds that that atom has a tendency to make. Okay, so hopefully that makes sense. So what's the kind of the moral of the story is it can be used to predict situations in which ultimately you may come up with more than one possibility you think maybe works. And as you guys are finishing up the worksheet for tomorrow, and as you're getting ready for the quiz, this is just another sort of tool in our toolbox to use, right? I use that term a lot. So here's kind of, I think, the summation kind of this, okay? So use formal charge calculations as another way of confirming whether your Lewis structure is correct. So it is just another sort of tool in our toolbox. Okay. And I challenge you to kind of go back through, and maybe you've got some of the work done on the worksheet. Maybe you're finishing up this afternoon, whatever. Take some time to calculate formal charges of the atoms, the individual atoms within the molecule, to see, do all the formal charges equal 0 for all of the atoms in the structure that you've come up with. Okay? Now remember, this little warning, right? It's about the total number of zeros, not the sum. Okay. So don't, let's just say, hypothetically, here's a molecule A and B, right? And I calculate the formal charge for this version. Let's just do this. Let's say it's A, B, C. This is better, okay? So that's option number 1. I calculate the formal charge of A in this case to be 0 based off of the rule. This one's -1 and this one's +1, okay? And then I have another, let's say I have another option that I come up with, C, A, B. Okay, I flip it around a little bit. Okay, I calculate formal charge for C is 0, formal charge for A is 0, formal charge for B is 0. Okay, this one's the better option. That's what I mean by this. It's about the total number of zeros. All of the atoms have a formal charge of 0, designating to me that they have the correct distribution. This one is bad because it has 2 atoms that have non-zero values. Okay? I don't add this up and go, well, +1 plus a -1 equals 0, plus 0 is 0. So the sum total of this is all 0, so it must be good. Okay, well, it's not, right? It's about wanting to hopefully have all of the atoms within the structure that you propose with a 0 value for all of them individually, okay? All right, so hopefully that makes sense. I think it does. I think I've explained that well enough. So this is pretty cool. Like, it's a way to check. Basically, what this is. It's a way to check your answers, to be honest with you. So use it. Use this to your advantage. Okay. Now, so this is the quiz cutoff point, really, at this point. Now, don't get me wrong. Like tomorrow, we're going to end up starting some other things. Okay. And moving our way into what do we got next on my list here? We're going to talk a little bit about what is it? Exceptions to the octet rule, expanded octets, some things to look out for in the remainder of the week. Okay, but this is the quiz cutoff point. Keep in mind, like these are, this formal charge calculation is just another tool. We've given you the connect the dots method to use. We've given and talked about using the steps that the book presents to you. using the skeleton structure and then distributing electrons. And then now we have formal charge calculations as a way to confirm if our structure that we've came up with is correct. Keep in mind on the quiz on Friday, right? You'll need to determine which method to use, right? Covalent bonding, covalently bonded, all non-metal atoms are going to be using dashes, and you got to show the dots of the unshared pairs. If it's an ionically bonded substance, though, you got to use, it's no dashes, right? You're showing the circles to show electron ownership. You're adding the charges in, like I taught you yesterday. And then you're going to color code anytime you have an ionic bond, right? So when we talked about when you do an image for an ionically bonded substance, make sure that you color code to show me bond or original electron ownership with the positive atom, okay? All right, I think that takes care of it, guys. Like I said, keep working on the worksheet. We'll see you. We'll see you kind of. I guess we'll be checking in the forum tomorrow for check-in. Oh wait, we're checking in the forum today. My bad. We're checking in the forum today, Tuesday. I'm ahead of myself. But I'll see your work tomorrow as you hand in your worksheet, and I think we're good to go. As always, if there's any questions, email me, let me know, ask questions in the forum, all that good stuff, and we'll get through this. Good job today, guys. See ya.